Buddy, Renaud, I cannot share my screen, but thank you everybody for your participation today for this webinar related to the optimization and lifetime extent of wind turbines. Today now I can share my screen. Perfect. It will be easier. Today we have three experienced speakers. First one, Tuv Sud, second one, Laborelec, and last one, Luminus. And after each presentation, we will have a bit time for questions and answers. Please put your questions in the chat. We will select all of them if we have the time, or some one of them if we have less time, and ask them to the speakers. And please also mute yourself if it's not the case. For information, this is the second webinar on this subject. We had already a first one in March, and you can see the video and the slides on our website. This one was with 5 other speakers. If you are looking for a partner in wind energy, please go on our website. You can have a look at all our members with some experiences in wind energy. And if you want a bigger overview, if I can say, you can also go on a website called riwalonia.be. And on this website, you can find a mapping of almost 80 actors in wind energy. And there is also a description of some projects, R&D projects, namely. 2 words about training and recruitment. The first one is about training from TechniFuture for people who are looking for a job. Maybe it can be interesting for maybe if you know somebody, but you can have a look at this after the presentation. And another information is about SVP production. We had a contact with this organization. In fact, it's 2 young guys who wants to make a video, a story, Une journée avec, called Une journée avec, which will last 15 minutes, and it's entirely free. If you want, you just have to contact them because they want to do this video and to share it with young people to give some ideas for future job. You have an email here on the slide, and you can also have a look at previous videos of them. A last word about our events. If you want, you can have a look on the website for our next event. And for example, you can find information about the event at the end of October about smart meters and energy communities, and also information about the event in the end of November about hydrogen and organized with Skywind. Wim?
Yes, hello everyone, welcome. My name is Wim van Kouwenberger. I'm the director of BEMAS, which stands for Belgian Maintenance Society. And I would like to take this opportunity to also introduce very quickly one of our activities. First of all, I also like to mention our corporate sponsors. So thank you very much for them. So you are in the control of the slides, Paul. So if I can say, just say next slide, please. Yes, so well, BEMAS, as I said, is a not-for-profit organization working on maintenance and asset management. We are a cross-sectoral actor, so that means that we have, well, in every industrial sector that you can think of, members in the food, the chemical industry, but also in the wind industry, we do, and like power generation in general. We do have members, and we closely work together with the cluster TWEED on the wind energy, of course. And so that's why we have also today this webinar. So So yeah, what's the idea is exchanging, well, ideas and exchanging thoughts. So one of the initiatives that we do have is a training cycle on maintenance and asset management, which is starting quite soon. It's every Tuesday, available in French for the moment. Unfortunately, the Dutch-speaking version is fully booked, so that's only possible for the next season in 2020, starting in September 2022. But we do have spaces available for the French edition. So if someone is interested in to learn more about how to increase reliability and manage the assets also in the wind power, don't hesitate to contact us. So next slide. Another very important initiative is a hybrid conference that we are organizing in Antwerp, taking place by the end of this month, so in a few weeks. And it's called Asset Performance 4.0. The major team, next slide. The major team is in fact, digitization in maintenance and asset management, and a lot of different aspects which I will talk about a little bit further on. But anyhow, it's quite a comprehensive program. We have 20 workshops which are more interactive and in-depth sessions. We have 50 exhibitors at the exhibition, so all in digitalization of maintenance. On the conference program, more than 70 presentations with 25 industry cases. So you see some of the companies, but there are many more. So I would say more information on assetperformance.eu. Next slide. And so you here see it's about asset performance management, of course, predictive and remaining useful life prediction, connected technicians, how to increase reliability, digital twins, even lubrication 4.0, a lot of different topics, all on digitization and maintenance. So next slide. So I would say if you want to discover the full program, more than 70 presentations, don't hesitate to visit the website assetperformance.eu. So I think that will complete, next slide, my introduction. So of course, if you want any information about Cluster-TWEED or BEMAS, don't hesitate to contact our Mr. Paul Bricot and my colleague Charles-Alexandre Lachapelle. Okay, so next slide. Yes, of course, because the next slide is in fact introducing the first speaker for today. I think that we have made a lot of publicity, and I'm very happy that we have with us Mr. Christian Schumacher. Hello, Christian, welcome.
Hello, Willem. Thank you very much. Welcome to the audience from my side as well.
Yes, so Christian, let's get acquainted first. You're in fact kind of the keynote speaker for today. The theme is lifetime extension of wind turbines. The question is here, how did you get interested in this topic?
Let's say the topic automatically came to us since we are, as Tuv Sud, dealing with wind turbines and certification of wind turbines for a long time, and especially in our home market in Germany, where the installation of wind turbines started very early, as we will see in the presentation in a few minutes. Automatically, the question arose, what's to do when 20 years are over? So I think it was already 4 or 5 years ago when we started thinking about which processes have to be applied to keep the level of security and safety when we continue operation.
Yeah, okay. And can you explain a little bit your role within Tuv Sud?
Of course. I am located in Munich in our headquarters in Germany. And here we mainly deal with the type certification of wind turbines. So we have lots of customers, the big OEMs, before they can bring their new turbine types into the market. We accompany them during the development of the types, and this finishes in type certifications. So my role, especially in this process, is the load assessment. So assessing the loads that then are used for telling whether all components are fit for the design lifetime or not.
Yeah. Okay. So, and then based on that experience, you're going to share your insights now on lifetime extension. So I would say, please take the presenter role and you can share your screen and your presentation, and we're very keen to learn all about it. So please go ahead.
Yeah, again, thank you very much, Wim. Thank you as well, Paul, and overall for the opportunity for us to share our experience in the field of lifetime extension for wind turbines here. Yes, as I already have said, I'm representing here Tuv Sud. We are located in Germany, in Munich, but as you can see, we have a couple of offices in all parts of the world. So if we can be of help to you and offer services in any projects, please get into contact with us and we will see if we can be helpful for you. Now, today we are dealing with the field of wind turbines, and in this respect, most of the work is located in Germany for Tuv Sud. So we have three main offices, our head office in Munich, where I'm located. And as we already have heard, our main aspect of work is type certification for turbines, also lifetime extension, as we will see today. And then we have two other offices. One is in the northern part of Germany, in Hamburg, where project certification of offshore wind projects is handled. And then another office in Bavaria, in Regensburg, and here more site-specific analysis like wind resource analysis, the optimization of operating wind farms, and also due diligence are topics which are handled there. But this was more in general about our experience in the field of wind turbines. Today, we want to focus on one specific issue, which is what to do when wind turbines reach their design lifetime. And just to give you a quick idea how we're gonna tackle this question, first I have a few slides to shed light on normative frameworks and principles, how which regulation exists, and also how the lifetime extension is handled in different countries in Europe. Then specifically, after we have learned which regulations there are and what their main idea is, we will have more detailed look into the actual elements of the analysis. And you already see there's analytical elements, there is a practical part. Both of them are important, and we will have detailed looks on each of them. And then at the end, the findings of both are concentrated, a final report is created. So this will be the end of the presentation then as well. So I already said in the beginning that if you look on the graph that I included in this here on the screen, we see how many turbines for selective countries in Europe reach their end of the design lifetime. And as you can see, Germany started rather early to erect turbines, so we were one of the first countries to be confronted with the question what to do then. Also Spain and Denmark were early adopters, so to say. UK as another big wind market still has some time until the issue will get more pressing there. And if you have a look at the regulations that exist in the countries, you would see that it's quite different. In some countries, it is mandatory to do certain assessments after the design lifetime. In other countries, there does not exist any such obligation. For example, in the UK or Spain, it's open up for the operator to decide how he will handle the question, how to keep a sufficient level of safety if he wants to continue with the operation. So this, in fact, has a direct influence on the scope of assessments that we conduct, since in markets where regulations exist, normally the customer want to, of course, follow these regulations. And for example, in Germany, then the scope of an RTE assessment is to confirm the structural integrity of the turbine for a certain lifetime. In other cases, for example, in Spain, where the customer does not come in order to fulfill a certain regulation, but rather out of own interest, the motivation is more from an economic side. So it could be that the assessment scope gets wider because it doesn't want to strictly have knowledge about the structural integrity, but also specifically for certain components, how reliable will they be for certain amounts of time. So the point here is that it depends on the market where we acting, what exactly the scope of the RTE assessment will be. Of course, apart from national regulations, there are also guidelines which handle the topic of lifetime extension from the typical sites like DVGL, UL. Of course, also there's an ainsi guideline, even if currently under the development, they're 61400-28. And they all have in common that they define which components are relevant for the assessment, and that the overall objective of the assessment shall be to assess the structural safety and integrity of the turbine in a comprehensive survey. Minimum requirements of the assessment are then defined, and I think the current date here is not. We don't have enough time to go into details of all these regulations, of course, but I think it's enough to single out one important thing that they have in common, namely that the assessment shall consist of two parts, being one on the one side an analytical part, in order to be able to answer the question, how long can I keep a defined level of safety at a specific site? So to say, look into the future, how long will it take for a specific wind turbine until the design loads are reached under specific site conditions? So this is the analytical part, the question that I want to be able to answer there. So this is purely theoretical. Of course, in theory, I can calculate that the turbine will be safe for let's say 25 years. And in fact, the maintenance has been weak, and maybe there have been failures during the erection process. And so you can be happy if the turbine merely survives 20 years. So in order to get a picture of the actual condition of the turbines, this has to be accompanied by a practical inspection of each turbine. And if you then take into account the findings of both elements, this is what is needed to have then the final results of the assessment. Okay, so now I think it makes sense to look specifically how the analytical part first and later the practical part is composed. As I already have said, now, first of all, let's concentrate on the analytical side. And the question that we want to be able to answer is, how long can I operate a specific turbine type at a site with site-specific conditions? until the design load level of this turbine type is reached. So in general, what we do, we make load comparisons. So we calculate fatigue loads under site conditions and fatigue loads under design conditions. We have a specific methodology comparing both in order to calculate the time that I can still use the turbine until the design load level is reached. But first of all, I have to get some input on the one side for the design conditions, on the other side for the site-specific conditions. And in the next chapter, we want to define what are the site-specific conditions that I need to know. Here, just a quick glimpse, maybe, so that you get the impression. In general, for LTE assessments, it is very beneficial to have a good documentation of the wind farm. We have certain informations that we definitely need to know in order to conduct the assessments, which is here displayed in green brackets. And then we have further information, which is nice to know in order to further improve the result. And in fact, to be able to compute higher lifetimes, even with the confidence that we need. And I don't want to go into each point here specifically, but definitely what you need to know, of course, is the wind farm layout, coordinates, commissioning dates, the type certificate, including the design conditions which we use, lots of yield data about changes of components, about the maintenance protocols, and so on. I think in the next slides we will then see where we need what kind of information then during the process. When we analyze the site-specific conditions, there are quite a few points of views and aspects that we have to consider and characteristics that will be evaluated. But with respect to the fatigue loads that we in the end want to be able to calculate, two of the influences should be singled out because they have the highest influence on the resulting fatigue loads. And these two site-specific conditions are, on the one side, turbulence intensity. You might be familiar with the turbulence intensity. It's, you can say it's the small timescale fluctuation of the wind turbine as well. And so just in speaking in general, if you have higher turbulences, you will have higher fatigue loads as well. We will have a detailed look on the actual assessment of the turbulence intensity on the next slide. But before that, I want to mention the second very important side factor as well. It's the frequency distribution of the wind speed. So of course, the more I have high wind speeds, the more energy comes into play and the higher the loads that act on the turbine. So you can say for sites with low wind speeds, they improve the potential for lifetime extension, even if it's not a good thing for the yields of the turbine. But on the happy side, you can at least gain some potential to be able to operate your turbine longer on places with weaker wind speeds. Okay, as I said, now we want to specifically look into how do we assess turbulence intensity and the wind speed distribution. The turbulence intensity is caused by two separate factors. First of all, we have the influence of the surrounding terrain and maybe buildings, settlements, forests, whatever might be around our wind farm. And you can classify all these surface types and give them different roughness length, which then will cause different amounts of turbulence intensities. And this is the so-called ambient turbulence intensity. You can either get the knowledge about the ambient turbulence intensity by conducting measurement campaigns, which in most cases is too much effort. And in most cases, we don't have access to such data for old wind farms. But the typical way to learn about the ambient turbulence is then to do it in an analytical way, to create these roughness maps where you classify the surface types in an area of maybe 20-30 kilometers around your wind farm. And then based on that and taking into account any settlements, buildings in the surrounding, the slopes come into play as well, then you can calculate the ambient turbulence intensity. So this is one important factor. The second one are the so-called wake turbulences, which are caused by neighboring turbines. Here we also have analytical approaches which can be used to calculate the turbulences that are caused by neighboring turbines. And you can imagine in cases where I have a wind direction and my turbine is in the shadow of a turbine in front of it. This, on the one hand, causes decline in wind speed, but then also it causes additional turbulences that act on my turbine. And so we have to take into account both of them, ambient turbulence, wake turbulence, and then we get the so-called effective turbulence intensities. And this is important input for our load calculations. Then the second important input, as I said, wind speed distribution. The scenario is quite similar, or the task is quite similar to when I am planning a new wind farm and want to get knowledge about the wind resource. But in the case of a lifetime extension, of course, I have the advantage that my wind farm has been operated for 19 or 20 years. So you can, so to say, use your wind turbines as big anemometers and use the yield data that you have recorded over the operating time in order to validate wind model that you can create using meteorological data sets. And this is a very useful method to, without using too much capacities, get good wind models for lifetime assessments. So at the end, the wind speed distribution can be defined by the so-called Weibull parameters. And this is what we are then working with in the following load calculations. A quick example to illustrate how detailed knowledge of the wind farm and its surroundings can help to improve the results. Let's assume that in the surrounding of your wind farm that you operate and you want to keep operating, maybe after 10 years of operation, another wind farm has been built. And let's assume that this wind farm was so close that the turbulence intensity for your turbines has been increased. So the result is here the displayed blue curve of turbulence intensities, which is, if you compare it with the assumed design level of constant 20%, rather high. Now, it's possible that if you don't have more knowledge than that, then you have to assume that the turbulence intensity follows this blue line, and you will get the resulting rather high loads. But in many cases, there have been mandatory sector curtailments during the authorization process of additional wind farms. So it could be that neighboring turbines have to be switched off in certain situations where they would cause too high turbulences. And if we have some proof that such a sector curtailment is active, we will take this into account during the assessment of the turbulences. And in the example case here, this would lead to the very much lower turbulence level you displayed in the green line. So far, we have seen what we have to do in order to get the necessary input information for the load assessment. So this is now the part with the load assessment is the part where we finally answer our interesting question: how long can I operate my wind turbine without surpassing the design load level? And we want to be able to answer this for each component which is relevant for the integrity of the turbine. Our tool that we use here in order to be able to answer this question are error elastic load calculations. In the next slides, I will explain how these are conducted. First of all, regarding the input that we need, you can see we need, since we want to conduct the load calculations for the site and for the design, and then do the comparison, we need the necessary inputs from the site that we just have seen on the slides before. Then the wind conditions for the design, they should be clear based on the input information that we got from the customer, meaning the type certificate and eventually load reports, maybe, to get all necessary information. So that's what is supposed to be at hand when we start with our calculations. First of all, we need a simulation model, which is composed of all major components of the wind turbine, of course. So we need to have information about the rotor blade, including aerodynamic properties, structural properties, stiffnesses, mass distributions, and so on. Same goes for tower and foundation, for the drivetrain, and also, if not physically visible, the controller of the wind turbine, which can have a big influence on the resulting loads. If we have all this, we can put the parameters into our simulation software and set up the model. What we will do then is, as I have said, conduct a series of load simulations, and we will do that 2 times, once for site conditions and once for design conditions. As an additional input, then we have turbulent wind files, normally 10 minutes long, and we have these wind files for average wind speeds beginning from cut-in wind speed to cut-out wind speed, normally in 2 meters per second steps. So at the end, we have quite a number of time series for each simulation. Each time series is 10 minutes long. Of course, you can then display the history of the wind speed at hub height, as it is shown here in the example. And in parallel, you have a history of the resulting forces and moments acting on each component that we want to analyze later on. Now, the question arises, how can I be able to compare these time series with each other, make a comparison between the time series for the site and on the other end for the design. And simply the time series by itself, they are not suitable to conduct such a comparison. And we have to do some post-processing in order to get some form of information that can be easily compared. And what we normally do then is, first of all, conduct the so-called rainflow counting, where all the cycles of each of the load sensors that we are analyzing are counted, and the amplitude of the cycles and the number of cycles. First of all, I can plot this like it is shown here. So the red line would indicate the design case, and the green line would indicate the site-specific case. As you can see in this case, the red line is above the green line, so this is the first indicator that there's some potential left for more operation until the design loads are reached. But of course, in order to do it mathematically and to get clear results, we further post-process also these collective loads. And with the concept of damage equivalent loads, we calculate this collective to a so-called single level collective, which would cause the same damage as this multi-level collective. And by using the formula that is displayed here on the bottom of the slide, and the right SN curve slope, depending on the type of material my component that I am analyzing is composed of, then I can calculate how much time in general or in total is left before the design load level is reached. So this is in theory, the process that we are following. Of course, in each project we have different tasks, different hurdles that we have to take. And in some cases, we are dealing with the problem that not all necessary input information is present. It could be, for example, that the customer cannot provide the type certificate of the turbine that we should analyze. And as I've said, this is a very crucial input information for our calculations, since we definitely have to make some assumption what turbulence level and what wind speed distribution has to be applied in order to calculate the design loads. So in these cases, we have to find some workaround, some source of the type certificate. And normally we can try to get support by the OEM, maybe also from authorities. And in some cases, we also can have a look at our archives in order to see if we have some useful information to get this knowledge, what type certificate can be applied here. Another possible problem could be that I don't have all this detailed turbine design information. When I was talking about the setup of the model, I showed that we need lots of specific information about rotor blades, tower design, and so on. And this is a problem which we have lots of times because the turbine models that we are dealing with are already quite old. Sometimes the manufacturer isn't active anymore. So it's in lots of cases it is hard to gain all this detailed information. So this was something that we had to solve beforehand, and we come up with a solution to use so-called generic load models. So this is not an image, a complete exact image of the turbine that we are analyzing, but it will have some differences by a study and a comparison with lots of turbine types. We gained knowledge about difference in behavior to to the input factors, and at the end, then we develop the process to work with these generic models, add some safety factors in order to be still on the conservative side, and then have a tool that we can use to analyze turbines where we don't have specific design information at hand. Okay, so this should be the first part, the analytical part. I think the part which needs most explanation. As I've said, it has to be accompanied by practical inspections as well. But these inspections, they are more or less similar to the inspections that have to be conducted during the original lifetime of the turbines regularly. So, of course, the scope is to have visual inspection and functional checks of each turbine, which, as I've said, is very similar to the normal inspections. What is special here is that we want to conduct a weak point analysis. So if we, from our experience, know that certain turbine types have shown to have problems at specific components, we would have a closer look and analysis for these specific components than at these projects. And since we have been working with a lot of turbine types and even have been certifying turbine types that now have reached the years of 20 years and older, there's lots of knowledge here when it comes to specific problems that might be caused by maybe design flaws or some manufacturing issues and so on. Besides the visual inspection, also an evaluation of the operational and functional safety system is part of the inspection. So we have a look at the pitch system, your system, do some emergency stops, check vibration monitors, and finally do some test runs in order to be sure that the turbines are all fit to be continued in operation. Normally, the findings on the sites can be concluded that most of the turbines that we are inspecting are in rather good condition, and often there are no big flaws which need to be corrected. Of course, you have cases where some corrosion exists, maybe like here on the left picture at the tower top flange, or cracks in the foundation. Depending of the extent of the cracks, you might need some sealing to repair them. Then on the right side, we see a collective pitch mechanism, which I think in this part was quite worn out and need some refurbishment. And also with regard to the electrical system, here was a case where the medium voltage switchgear didn't have sufficient pressure anymore. Of course, all about the connections are checked, at least visually, of course, visually, also acoustically, if there are any suspicious findings. And in case yes, then the torque moments need to be checked. Then I think on the right side, we have a weld seam of a door frame, which also shows some corrosion that should be refurbished. In some cases, we also see missing bolts, sometimes on the rotor blade connections, which can be a weak point with regard to the lifetime extension. So this is, of course, something that needs to be corrected immediately. But as I've said, in general, the condition of the turbines, which have a good maintenance concept, is sufficiently so that only in a very small amount of cases, immediate action is necessary, and the practical part does not pose a hurdle for continued operation. So once that both parts have been conducted, the practical and the analytical part, what are the next steps? Of course, the first question that arises is, are immediate measures necessary? This could be if you have, in most of the cases, if there are findings in the practical inspection, which might compromise the safe operation of the turbine. Of course, then we have to say the operation needs to be stopped until this problem is solved. As I've said, in very few cases, this is necessary. It's also possible that from the analytical side, we come to the conclusion that already the analytical or the theoretical potential is used up, and that you immediately, then it depends on the component which is affected, that immediate action is necessary. Yeah, this happens rarely. Of course, if you have a turbine which has been erected at a site where it's in reality was designed for weaker wind conditions than happened the 20 years of operation, it can be that theoretically you're already at the end and you have to exchange certain components in order to keep operation active. In general, what we do is that based on the analytical findings, we can give each relevant component an additional lifetime until the design loads are reached. So this will be reported. Furthermore, we can give solutions in order to further continue operation of the turbine then. For example, and then it clearly depends on the type of component which reaches the design load. One solution can be to exchange a component, maybe for certain voltage connections. This is possible without much effort. Then there might be other cases where this problem can be solved by shortening certain inspection intervals in order to check if some damage might occur. But clearly this depends what type of component is affected, if it's visible and reachable, how much effort it means to exchange the component, if there are other solutions possible or not. And depending on this, the future inspection intervals are defined. And yeah, then the operation of the turbine normally can continue. Okay, so this was my presentation so far. And now I'm
thank you
to answer your questions.
Yes, thank you, Christian. There are quite some questions, so we are kind of in a time constraint. So please answer quickly, if possible. So first question here. Okay, so what is in your opinion, your experience, a typical potential for an extended lifetime?
Yes, so based on our experience, I would say 70 to 80% have a good potential for continued operation, and the operation will be over 25 years in total. Even 30 years are something that we see in many cases.
Yes. Okay. So that's very specific. One of the things you said is that there are different regulations in different countries on lifetime extension. And the question is, are you aware of the Belgian wind farm regulation? What would be here applied? Are there any obligations, yes or not, after a 20-year?
Unfortunately, I can only say that I am not aware of any national regulation that would exist. Maybe some of the audience knows better than me, but so far as I know, there's no specific rule to follow here.
Yes, of course, you do have a kind of responsibility when something goes wrong. There's also worker safety. So anyhow, I think after some time you need to do some risk analysis. So, but anyhow, let's invite people to answer the question if they are aware of. Maybe it's different in the different regions in Belgium too. If you consider the lifetime extension, you have, of course, one side, okay, what is the technical lifetime of the windmill? But on the other hand, you have also, of course, they have also the offer of new technologies that maybe offer more higher efficiency. So is that also put into the balance when evaluating the potential of lifetime extension?
It depends on the solution that could be imagined, because there might be room for improvements with respect to the yields of the turbine, but you always have to keep in mind that you don't want to change the loads that are produced for the turbine, because this is important that the turbine behavior was checked during the type certification. And now if you do certain enhancements which then rise or increase the loads that act on the turbine, operation might not be safe anymore. So I would be, it depends on the actual solution.
So increasing load is a difficult option, but okay, maybe replacement rather than a lifetime extension. How do you evaluate that, one against the other?
Yeah, clearly, in many cases, the replacement of certain components is a good way to reach additional lifetime. But I think at the end, this then leads to an economical question: how much costs arise from the replacement, how much money can be earned by further operating the turbine. So this is something which is hard to cover from our side, since we only are dealing with the technical aspects. Yeah. And okay. Of course, depending on the market you're operating and depending on the prices that can be gained for the produced electricity, this might be different even from year to year, I guess.
Yeah, okay. So I have a question about one of the slides. Maybe you can go there, but there were SN curves in red and in green for the load. So can you just explain the different colors there? I think it was this one, yes.
Yeah. So what we did there, as I was explaining before, first of all, we gather lots of data by simulating time series for the design case and for the site-specific case. So with site-specific turbulence intensities and with design turbulence intensities. And then let's say we count up the load cycles, for example, at the rotor blade root. And what can be seen here is for a specific amplitude of a load cycle, let's say 8,000 kilonewton meters, you can see how many of these cycles are collectively counted for the green site case and for the red design case. Oh. So you can say, okay, then I have 100,000 cumulative cycles, and in the site case with an amplitude of maybe 7,800. In the design case, it's an amplitude of 8,200, and that leaves some space, some potential for further operating the turbine.
Yeah, okay, so thank you. Yes, we have some. Yes. If you want to, I would like to maybe ask a few more questions, but very quick answers, please.
I try.
Okay, yeah. So, okay. Have you experience with lifetime extension of offshore wind farms?
I think no, not so far as I know that we have been dealing with that.
It's related also with the age of those wind farms, of course. And then it's one of the questions here. When is the good time to start with thinking about lifetime extension? when do you need to start the process? What do you recommend here?
Okay, so in general, not shortly before 20 years are reached, but sometime earlier, maybe after 19 years, after 20 years, after 18 or 19 years, to leave some time in order to make clear what is needed, documentation, and so that then you can have a smooth project and get the report in time. And of course, it could make sense in some cases if you want to have an early knowledge about the potential to at least conduct the analytical part even earlier. Of course, then at the end, you need the practical inspection once the turbines are 20, but you can have a hint of your potential for lifetime extension earlier if you maybe conduct it after 15 years already.
Yeah. Okay. So what about generator and gearbox inspections? Do you also assess during a lifetime extension assessment?
Yes, normally they are inspected by visual inspections. Of course, if there is a reason to go into more detail here because there have been problems with these components, or you know that for certain turbine types they could be problematic, we can also offer to do deeper inspections for these components.
Yeah. Okay. So in general, because of course, what is the business case of such a lifetime extension? Saying, okay, what is the cost in fact to perform such an analysis as you are proposing? Does that depend on the size of the windmill, or is there the wind turbine, or what are, well, the costs related to such an analysis?
So you can say that there's a high scaling effect, since if you are only analyzing one single turbine, you have to do a certain effort to at least do the analytical part. And then if you're dealing with a complete wind farm of maybe 20 turbines, you have to do a little more. Maybe it's sufficient to do maybe 2 calculations in order to judge all the turbines, because you don't have to calculate each turbine individually, since the site conditions are in most cases rather similar. So there's lots of money to be saved if we don't look at individual turbines, but on wind farms. And the larger the wind farm, the more cost effective the whole thing gets. Of course, one thing that still has to be done for each turbine is the practical inspection.
Yeah. Okay. And so what kind of budgets are we talking about here?
I think for a single turbine, the complete package might be around maybe 8,000 to 10,000 euros. And then if you have a whole wind farm to be analyzed, the scale effect will come into play in a big way. So let's see this for the individual wind farm, but yeah, I think it's not too cost.
Yes. Okay. Yeah, but you gave an idea for one single wind turbine, so then if people are interested, they can contact you.
Absolutely.
Christian, I've seen that there are some more questions in the chat, but I propose that you have a look at them and try to answer in the chat if you wouldn't mind, because due to the time, I propose to hand over now the presenter role and the moderator role to Paul, because he is going to introduce the next speaker. Please, Paul.
Perfect. Thank you.
Thank you very much, Christian.
Thanks a lot, Christian. We will now have the pleasure to listen to Laborelec and more precisely to Julien Masson, R&D expert, wind expert, and maybe also to Elmar Knauf. Julien, are you there?
Yes, we are here. Yeah, hello.
Perfect. Hi. Can you share your screen and your presentation?
Of course, yes.
Perfect. And my question is, of course, not a surprise. How can we improve the performance of wind parks. Thank you very much to you.
Yeah. Thank you. Hello, good morning, everybody. Thank you to you to give us the opportunity to present Laborelec's wind services, more focused on performance. We have, of course, a lot of other services in our department, but the theme of the presentation of today is how we can improve the performance of the wind farms. So we will start and we will explain how what is the yaw and the pitch misalignment, and what are the consequences of this misalignment on the wind turbine. But let me first of all start with a short introduction. So my name is Elmar Knov. I'm key account manager in the wind department at Laborelec. And I worked on several positions in the group. I have more than 2 years experience as a wind construction manager for offshore and also for different IV projects. And Julien, maybe you can also introduce yourself.
Yeah, of course. So I'm a mechanical engineer and renewable energy engineer, so specialized in wind. I work since for 3 years at Laborelec in the wind energy team. So I'm a project manager here, and I mainly work on data analysis project for R&D purpose to optimize the production mainly of our assets.
Okay, so as you know, we work for Laborelec. Laborelec is a part of the NG group. Laborelec is founded in 1962, so approximately 60 years heavy experience. We are more than 280 specialized PhDs, engineers and technicians, and our headquarters is here in Belgium in Linkebeek. We have also 4 other offices in the world, one located in the Middle East, in Chile, in the Netherlands, and also in Germany. We are, what I will really focus, and this is the most important on this slide, it's that we guarantee a completely independence on our studies. So that will say everything is not shared, nothing is shared in the group. So we are really very independent on this time. This is just a quick overview over all the activities of Laborelec, but I will not go too far in the details. I propose that we deep directly in the theme of this presentation. So what is yaw misalignment? Julien?
Yeah, so yaw misalignment is on the performance that can occur on the wind turbines. So to understand what yaw misalignment, first you know that probably you know that the wind turbine nacelle is following the wind direction. So the idea here is, of course, to produce the maximum amount of energy, and as well decrease, or at least not increase, the fatigue on the blade and on the turbine. So as you see on the image on the lower left, most of the time normally the turbine is aligned with the wind more or less perfectly, but it occurs that for a short amount of time or for longer amount of time, there is misalignment between the wind direction and the nacelle direction. So here
Julien, I'm sorry, but the sound is not very good. Maybe can you speak a bit louder, or
Yes, is it better like that?
Yes, I think. Thank you.
Okay, so I get closer to the mic. Okay, so basically yaw misalignment is the misalignment with wind direction and nacelle direction. And here you see, so you can qualify it with an angle, and that's basically what's represented here. So again, when is this misalignment? We say there's a yaw misalignment. Could be either static or dynamic, meaning that if it's static, there is always a static offset in between wind direction and nacelle direction. So it's kind of permanent static offset. So you always have this error. But if it's dynamic, it's qualified, it's more linked with the contour, which means the time that in between the nacelle position that reach the wind direction. So it could be too slow, could be too fast. But here we will focus on the static yaw misalignment. So there is a production loss linked with the yaw misalignment. And of course, the idea here is to understand a bit better how to detect and correct it after, and to get an idea of the proportion of the production loss. It's about 1 to 2% AP, but it's linked actually with the angle, of course, of the misalignment. And you can link it with the cost function cube or square, and you get the kind of figures. But typically we will speak about 1 or 2% AP. So what are the causes of the yaw misalignment? Basically, it's linked with the wind vane. So the wind vane is this instrument on the top of the nacelle that gives to the controller the wind direction relative with the relative wind direction. So the difference between the wind direction and the nacelle direction. There could be some issue with the wind vane. It could be hardware. So it could be linked with the error at the installation or during maintenance. But it could be software as well. So there is an offset that is set in between the value of the wind vane and the value used by the controller. This offset could be wrong, or because of a software update, for example, that erased the offset in the controller. So it's typically software issue. Or for example, imagine you install aerodynamics add-ons. It could have an influence on the wind vane, and sometimes they don't adapt the software parameters. So then you could create a yaw misalignment. And so we'll speak about another issue that could arise on turbines during operation. It's a pitch misalignment. So the pitch misalignment, it's again linked with angles, but this time it's the angles of the blade. So the blade can rotate on themselves. That's the movement that is described in the picture here with the 3 arrows. It's used to slow down the turbine, so brake the turbine. It's an aerodynamic brake. It's also used as well with low wind speed to catch wind speed, but just the angle of attack. So the pitch is used, as I said, to adjust the angle of the blades with the relative wind that is velocity that is seen by the blade. So it's linked with the angle of attack, and so the lift, and so the production. Basically, the pitch is set to 0 degrees during most of the operation time of the turbine, and is used. So the angle is set to a higher value when we reach the rated wind speed, and so we brake the turbine and set the pitch to keep the power to the maximum power, the rated power. So here, for example, megawatt. So most of the time, let's say, normally the 3 blades should have the same pitch angle at the same time for most of the turbine. And there is a tolerated difference according to the NV here between 2 blades of 0.6 degrees. But it happens that the difference is higher, and so you have a pitch misalignment. So that's what we call a pitch misalignment. So for example, 1 blade has 1 degree more than the 2 other blades. That would be a misalignment. It is not seen by the controller, and the controller have the same 2 value, but in reality there is a pitch misalignment. So it's quite frequent. So we have, for example, here external study from a service provider that is measuring on site pitch misalignment. He measured more than 4 gigawatts of turbines, principally mainly in France and Europe, and he found out that a bit less than 25% of the turbines show higher than 0.6 degrees between 2 blades. and so suffered of pitch misalignment. From our internal studies with on-site measurements, over 84 turbines measured in France and Belgium. We found out that 27% were higher 0.6 degree. So it's quite frequent. And there is, of course, an impact. So the impact on AEP, we measure it on a case. This case was in Belgium. We actually detected a pitch misalignment on one turbine and required the OEM to correct it. Unfortunately, the OEM didn't correct it properly the first time. So, and we had to call them back and they had to correct again. And so that left us with let's say 3 different periods and we could compare. And so the first time that they performed a wrong correction, the AEP diminished by 1.5% according to our LiDAR analysis. So we had a nacelle LiDAR mounted on the turbine. And after the good correction, let's say 6 months later, we got back the loss in production, more or less. So there is an impact on AP, which is kind of logic because you change the angle of attack of the blade. And it's about 1%, let's say, in this practical case. That was, for your information, 2-degree pitch misalignment. And there is an impact on vibration and so lifetime. The impact on vibration here, you can see the high decrease of the vibration level. So this is the same case than I showed before, same turbine. And here we show the period just before and after the correction, good correction that happened. So the second correction by the OEM. It was a 2.2 relative pitch misalignment. And you see orange and blue, it's 2 vibration indicators. And both decrease right after. And in green, you have the wind level in meter per second. And so you can see that there is a straight link between pitch and vibration, pitch misalignment especially. And that's what we will use to detect it. But I'll leave Elmar continue with the yaw.
Yeah, thank you. So Julien explains what is a yaw misalignment. But the question is now, how can I detect, how can I know if I have a misalignment, or what can I do to correct this fact? So the first, what we advise at Laborelec is to perform a yaw scan. So the yaw scan, we at Laborelec, we developed an in-house software to scan all the wind turbines of a wind farm, for example. So what we need to receive the SCADA data from the machines. So ideally the 1-minute SCADA. But I know you have all the machines, I think more than 10 years. And then you have only 10-minute data available. And that's, we do the test in the past, but it was not accurate enough to do this analysis. So what we need is really a 1-minute data. And then we can perform this yaw scan. With this yaw scan, we will have directly a first results to know if my machine, if my wind turbine is misaligned, yes or not. Then the next step is to do a measurement. So what we can do is, once that we have identified the machines where the problem appears, we can install nacelle-based LiDAR to how exactly the misalignment of the machine is. Once that is performed, the LiDAR on the nacelle is placed for approximately, I think, 2 weeks to do this measurement. And then the last step 3 is then to correct. We can correct or on the software So as Julien say, on the controller, if there is the problem, or we can also do a change on the hardware. So for example, the wind fans. So that's really the steps to do for the misalignment correction. So here some pictures of nacelle-based LiDAR. There exist different types. And here some figures that we have from analysis that we already carry out at Laborelec. So we scanned 360 wind turbines. Of this 59, sorry, we have just over 20% of the wind turbines, they were misaligned. So that's 86 turbines. From these 86 turbines, 62% had a yaw misalignment than more than 4%. If you remember the graph that previously let's show by Julien, you remember that the production losses for 4 or 5%, we have approximately 2% of production losses. That will say for if we perform the correction of this misalignment, we saved more than 4.5 gigawatt hours a year of power for the owners of the wind farm. That's of course a huge figure, but you see directly that it is interesting to perform this yaw scan at first step. Now, Julien, maybe you can.
Okay. So let's continue with the pitch misalignment and how to detect it. So as I showed before, there is a link with the vibration and the relative pitch misalignment, and so that's what we will use to detect the pitch misalignment. We can detect with the SCADA data, and we use the vibration of the tower to get an idea of an indicator that would show the severity of presence of let's say the probability of the presence of a pitch misalignment. And so we compare the vibration level for certain indicator of the turbines in the park, and we can detect which turbine are the show the highest probability to have a pitch misalignment. And so afterwards, as for the yaw misalignment, we would go on site and make some site inspection with, for example, a laser measurement, and get the precise measure that would be applied to correct the pitch angle. So sometimes the challenge is to get access to those tower vibration SCADA tags, and depending on the OEMs, we have or not access to these values. So once on site, once the turbine are detected, the suspicious turbine at least are detected, then we can go on site and use either a photometry, that's what I will describe on this slide, or either laser measurement, would be for next slide. So the photometry, basically you have to stop the turbine, then adjust tip template on the blade. That's what you can see on the top right picture. And then make some different precise picture and adjust or look at the angle of this template compared to a reference. And according to that, you can know if there is a misalignment between the blades. And if you have the design of the turbine, the blades, then you can know if there is a misalignment with the absolute value, the design value of the pitch. This is quite long. It takes at least 1 day for a turbine, or let's say 1 day for one turbine, and you have to stop it. The second option is a laser measurement, and then it's quite fast option. You can measure one turbine in about 30 minutes. That's the option we used to measure 84 turbines in France and Belgium. It's quite useful because it's quite fast. You just have to go in front of the turbine, and then the turbine planes. The turbine is still operating, and the blades are passing through the laser, as you can see maybe here on the lower right image. And then there is the profile, let's say. It's not the perfect profile of the blade, but the same profile for the three blades. So you can compare and get a relative difference of angle. That's how it's used. And then in the end, you can retrieve which blade is misaligned compared to the other one, and apply those offset to correct the pitch misalignment.
Yeah, now some conclusions. As explained, you know now that yaw and pitch misalignment have an impact on production, and especially pitch misalignment has an impact on lifetime of the turbine. The yaw misalignment doesn't change over time, so that's something that appears directly from the start of the lifetime of the turbine. Performing a yaw scan for us is a good way to identify a misalignment and to save your money. So that was it from our side. We tried to respect the timing. So I don't know, I hope, are there any questions?
Thank you very much for your presentation. We have received some questions in the chat, but your presentation was very clear, so we have only a few of them. Of course, we have received some questions about misalignment. Maybe a first one. What are common causes for the measured misalignment, and how can you avoid them? And maybe also how to choose between software and hardware correction.
Okay, I can start maybe with the pitch misalignment, because I did not detail why it happens. Either what we see is during the construction of the wind farm, normally the TC mark of the blade should be aligned with the TC mark of the bearing, let's say. So the 0 degree of the blade should be the same that the zero reference on the gear, and that is verified during commissioning. But it happens sometimes that it's not, let's say the offsets applied are not the good ones, and so there is a pitch misalignment from the beginning of the lifetime. That's one option. A second option, and that's what happened on the case we presented. It was a maintenance on the hydraulic cylinder of the pitch system, but they didn't calibrate the sensor afterwards. So they created a slight misalignment for this blade, on which they did the maintenance on this cylinder. So I would say, to avoid this kind of issue, probably at commissioning, it's a good idea to measure the pitch misalignment with a dedicated tool on site. I would say that would be a good option. And during lifetime, probably have a close look at the maintenance and what's happening on the turbine. And if it's not detailed in the report, maybe contact the OEM to get sure that all the processes are well followed and that they calibrate the sensor if needed. So that would be for pitch misalignment. Mm-hmm. For the yaw misalignment, then we detailed quite well how it happens, and it could be, so again, software with a software update, for example, that you raise the offset that is applied in the controller. It's could be hardware as well, but anyway, for the correction, most of the time we do it software. So we get the value that should be applied, and we cancel the static misalignment with the contrary value, with the opposite value in the software. That's most of the time how we correct it.
Okay, thank you. Still about misalignment, but maybe a more quickly answer. does the probability of misalignment increase with the age of the wind turbine, and if yes, to which extent? Sorry.
Well, let's say not especially linked, but of course, the older is the turbine, the more maintenance operation it got during lifetime, and so the more probability there was a mistake during the maintenance. So, I mean, there's no direct link, but the more you maintain it, the more there is operation on it, the more you have probability to get errors or mistakes during those operations.
Yeah, and you have also an aging on the different parts of the wind turbine due to the misalignment of the yaw directly.
Thank you. Maybe a more general question to change a little bit. What is the most recurrent problem at the end of life of wind turbines, and how can we anticipate it?
So the most occurrent in between pitch and yaw?
The most frequent problem at the end of life of wind turbines.
Yes, Paul, I don't want to interrupt, but I think that was a question for the previous speaker, in fact. So maybe you can go for the next questions here. Someone is suggesting here to monitor the yaw error on the turbine with the turbine SCADA system. But does that cover detecting all the problems or not?
So yeah, that's what we're kind of doing. We're monitoring the yaw misalignment. I'm not sure I understood well the question, but we use the SCADA data to detect yaw misalignment, potential yaw misalignment. Yes, it is now getting to be implemented on NG turbines with let's say real-time monitoring, so that it's assessed every week for each turbine of the fleet.
Yeah, and of course, pay attention to calibration. Huh? That's also one of the lessons you answered earlier. So if you don't calibrate the sensors, of course, you get wrong data in the system. Then maybe a final question here, Paul, and then I'll hand the word over to you again. But so could you could it also be that wear in the planetary gearboxes causes an increase in pitch and yaw misalignment?
No, I would say no, but what could happen for pitch misalignment? You excite some frequencies and vibrations as well, not especially on the structure itself, so the tower, but as well in the drivetrain. And so we think there is a link in between pitch misalignment, the severity of pitch misalignment, and some issues on gearbox and drivetrain more generally. So main bearing issue, for example. We are studying it, but we don't collect it enough statistical data to get some relevant figures, but we're still working on that.
Yes, thank you very much, Paul.
Yes, perfect. Maybe now we can listen to our last speaker, Maxime Kelder from Luminus. Are you there?
Yeah, I'm there. Hello, everyone.
Perfect. You can share your screen and give us a presentation. Thank you very much.
Yeah, thank you, Paul. Today, I think I will speak a bit less of techniques, will be a bit more abroad. Why? Because Luminus, if you don't know, is a producer as well as a supplier. We have a large fleet of onshore wind turbine in Wallonia, but also in Flanders. Today, I would like to present you, let's say, our two oldest Walloon wind farms.
Maxime, I'm sorry, but can you maybe change your microphone? The sound is a bit strange.
That better like this?
Yes, maybe.
Okay, perfect. So today we present you the two wind farms we'll talk about, and I will talk about the two possibilities we have. With those wind farms, I exclude a third possibility, which is dismantling the wind turbines and don't put anything else afterwards. So this is not a possibility for us. So the first possibility will be the lifetime extension. By lifetime extension, I mean go beyond 20 years of operations. And the second possibility is repowering of the site. So it means that repowering, it's important to define it. Sometimes there is some confusion. In wind, when we talk about repowering, I mean that we dismantle the old wind turbine and replace it, not especially in the exact same position, but on the same site with a new wind turbines. So we remove everything and replace by a new project. That's the definition of repowering. The two wind farms we will consider today are the wind farm of Villers-le-Bouillet and Walcourt. These are two wind farms that have been built kind of the same time. Commissioning date are in 2005, so it's 16 years ago. They all have the same turbines. So this is a MD77 platform, which is a repower system. It has been bought by Senvion, but now Senvion went into bankrupt. This is 1.5 megawatt platform, so that kind of huge capacity at that time in 2005. Above 85 meters, and the design lifetime of those wind turbine was 20 years. Generally speaking, what we know about wind turbine that they are in quite good conditions. We did a study like the one that has been presented by the Tuv Sud in the first presentation today. We did that kind of the study, and we know that theoretically they should last at least 20 years of lifetime. So it means that that can operate safely up to 25 years or even more for some of the turbines. It means that I'm not talking about the major components, which are generator, transformers, gearbox, and so on. I'm talking about the structure of the wind turbines. So I mean the tower, the nacelle, the hub, the blades, and all the connection in between. So we know that all of them should last at least 25 years.
Maxime, I'm sorry, but I had some message in the chat. Maybe you can put your microphone off and just use the computer. The sound will be maybe better.
Yes, it's good like this. Thank you very much.
It's okay. It's okay, Maxime. You can put you can share your screen again. Sorry, everybody. It seems Maxime has lost his connection. Maybe we can have a little pause and try again in a few minutes. Maxime?
Yes, he's back. He just get inside.
Perfect. Thank you.
Do you hear me now?
Yes, better. Thank you.
Yeah, thanks. Sorry for that. Okay, I'll share my screen again. Do I have to come back a bit, or is that okay for you?
No, it's okay. You maybe full screen. Yes, perfect.
Yeah, okay, perfect. So what I was saying, that structurally speaking, they can last 25 years. That's a good point for us. The major issue we face with that platform, this is specific to those sites, is the spare parts availability. This is due to the technology, actually, because it was Senvion. Senvion was into bankrupt 2 years ago, something like this. And then we know that some parts are quite difficult to find. So we always have to to play or to repair them, to find let's say not standard solution for continue operating with a high rate of availability. Today we will talk a bit of the strategy we have for extending the lifetime, but pay attention that the strategy we will present today is really specific to those sites and specific to the platform. So it could be, and I think it should be really different if we are talking about another site with other turbine types such as Vestas and Enercon or other major players in the market. So the first solution we have for those wind farm is the lifetime extension beyond 20 years. 20 years, why? Because the design lifetime was still 20 years. And then we know that to go beyond, we have to do some kind of study. The Belgian climate is not that severe actually. And then the assumption made for the 20 years of lifetime, initial lifetime, was with more severe conditions. So if we compare the historical data with that, let's say, those hypotheses of the standard lifetime, we know that we can go beyond that. The pros of extending the lifetime is regarding the environmental impact. So it is always better to use a viable and technical turbine that can operate than to replace it by a brand new one. So environmentally speaking, this is better. If we consider that the investment necessary to sustain the asset will be much lower in terms of megawatt, the price per megawatt hour produced than a full new one. So there is less cost for the collectivity because today, for instance, for Wallonia, with all turbine, we have no subsidies. But if we build a new one, then Wallonia gives us a bit of subsidy. So for the collectivity, it is indeed more interesting having old wind turbines. The third point is we also play a big role by sustaining those capacity more than 15 or 20 years in Wallon to help them to reach the objectives of the country in terms of renewable assets. In terms of counts, then yes, we know that we will for sure need extra OPEX or CAPEX depending on the strategy on the old assets, and then for sure we will have then less revenue. We know as well that as it is old, then we have a higher risk of unplanned maintenance of cost, and especially on that case because we have some of obsolescence issues that there is a risk of cannibalization. What does it mean? That, okay, if you know that we cannot encounter easily spare part on the market, and there is one wind turbine who cannot be operating anymore, we will maybe remove one wind turbine and use the spare part of this one to help for continued operation of the others. This is a risk that we have to take into account in the analysis. There is one point: can we, as an operator, transfer the risk to a third party? Some of time we cannot, and if you find a player who wants to take the risk, it will be too expensive. So most of the risk has to be taken by the operator of the wind turbine, let's say. For sure, as it is long, old, then you have higher risk of downtime, as it is old, and as you have a difficulty to find spare parts, then you have to foresee to adapt maybe your production in the future. And then based on that, you have less availability of the wind turbine. Also, another one is you have to adapt your maintenance strategy. For instance, in the past, you can find easily, you can have an omnium maintenance contract until 15 years with a company. In that case, you cannot do that. And then as you take a risk, you have to adapt the maintenance strategy. And then you maybe have to to have some capex, some opex cost, who have some provision for the future. And last but not least, yeah, in order to go beyond 20 years, at least in Wallonia, but it's true, I think, in a lot of different countries, you have to extend right. For instance, the old permit in Wallonia was only 20 years. So you only 20 years, the right to operate only for 20 years. If you want to go beyond that, you have to request an extension of the permit. So it's not that easy in the context of wind today in Wallonia. We know the permit rates are not that high for the moment. So this is a risk to take into account. It is the same thing for the grants. In our case, we don't buy the grants. We have kind of rent, so we have to extend the duration of it. So it's not technical, but this is important to have a turbine in operation, let's say. The big question is, okay, knowing everything that we talked about just before, we have a business case, let's say. I will not take into consideration, let's say, the price of electricity we can see today or even since a few weeks, but I will just take into consideration, let's say, the BEMAS of last year, which was 32 euros per megawatt hour. If it is that case, if this is the forecast we have, and we know that the OPEX will be kind of higher than before, does that revenue will cover all my OPEX? It's not that an easy question, but it has to take into account. And then if there is no support, let's say, or if there is no higher income than that figure, for instance, most of the operator will just do a run to fail. That means that we'll not do a lot of OPEX, we will not repair everything, and then we just wait the day that it will become not interesting to repair the machine. So that's a risk. So we have to be kind of sure of what will be our income until 25 years. The second thing is we have to choose between two kind of strategy in terms of maintenance. Or you choose, let's see, basically to have a small capex and 15-20, and we have a really huge OPEX. So you just give a contract for maintenance, much more maintenance, much more operation, and so on, and you try to put as much risk as possible in a third party, which will in any case be every kind of risk. Or you, let's say, prepare kind of capex. I mean, it could be strategic spare parts at this year in order to prevent any large downtime in the future, and then you decrease your OPEX, let's say. So this is two kind of strategy, and it has to be chosen or let's say a study for knowing what we will do in the future. The second solution is repowering at year 20 or even later if you don't have any permits. But historically in Wallonia, the rules that were applicable at 15 to 20 years ago for having a permit for wind turbines were not at all the same than today. So for instance, in Wallonia 20 years ago, it was possible to put a wind turbine at 350 meters from a house, which is today kind of impossible. Nobody will give us a permit for putting a wind turbine that close to the house in Wallonia. At that time also, noise regulation was a bit different. The constraints regarding the aviations, the radars and so on was different. The knowledge on biodiversity was different. And then it was possible to put a wind turbine close to, let's say, high risky site of bats, let's say. But today we know that it will be impossible to get a permit. So sometimes repowering, so requesting a permit at the same location will not be possible. So sometimes this scenario is not possible for all our old wind farms. For those two sites, the good point of repowering that is we we suppose that a priori the acceptability will be better because they live for 15 years with a wind turbine. They know what is a wind turbine, so we expect that the opposition will be lower, and then the permit obtention will be easier. That's what we suppose. Another point is, okay, we know that for these two wind farms that with the same site, we can expect to have, let's say, time 2 in terms of production, in terms of megawatt installed. It could be more for repowering project, but on that site, it will be only time 2. Why? Basically, it is because we have kind of limited tip height due to aviation constraints and radar, and also distance to Oasis. So we know that for those sites, we will be limited to 150 meters in tip height. This is quite important because today, if you look at the market, the turbine that you can buy in Vestas, in Aircon, Nordex, and I don't know who, but the best player in the world, you see that this kind of wind turbine become a niche market. So the price of such small wind turbine is quite high. And we know that the subsidy in Wallonia, which is currently necessary, it will decrease over the year. So it may become that even if we get a permit with that kind of dimension on those wind farms, maybe it will be impossible or even difficult to invest in such small turbine for repowering those sites. So that is important. The second thing is that we see more and more, and we have to assess also the grid limitation on those wind farms. So we need, at least for one of the two, we know that we have a huge grid limitation. So it means that there is some congestion, and it will be hard to inject more than today because the cost behind the grid will be really high, and then it will limit that. And then you have a huge production loss on your business plan. Other point is, okay, we know that you cannot reuse everything if you put a new wind turbine on the site. So it's not always possible to reuse a cable because they are maybe too small. The electrical cabinet, because this is not compliant with the standard today. The foundations cannot reuse it because you will put, let's say, a bigger turbine with different loads, so we'll not be able to use all, let's say, the balance of plant. So it's not that good. For those wind farms, Walcourt and Villers-le-Bouillet, the biggest constraint is the tip height, as I said, due to both aeronautical constraint and the distance of the houses, which is ruled by the 4 times. There is a mistake. It's not 4 times the diameter; it's 4 times the total height of the wind turbine. So one point, so repowering, it's not always a good solution, or it's not always a solution based on that. What I want to come with is each site, each old wind farm is specific. So there is not a standard solution for the question of lifetime extension or repowering. This is every time a new question and a new way of answer that question. But we know that we have to think about it as from year 15 at least. This is a good moment to choose between the two solutions. But however, at that time, we have a lot of questions that remains with a lot of, we don't have any answer to all of that question. The question, what are important is what will be my OPEX beyond 20 years? I have no idea sometimes. It's kind of difficult to answer. What are the possibilities of repowering? We can answer that question, but it is important to have a clear idea of it. What will be the support scheme of repowering for extended lifetime? So I know in Wallonia they are thinking about, do we have to give a small support to the operators to extend in the lifetime? Because it may help for reaching the objective of the region. What will be the new losses for my repowering project? That we know that today we have much more losses in terms of biodiversity, in terms of grid, that we never encountered in the past. So, and every year that comes, we see the losses increasing. Yeah, the next one is just what I said already. What will be the price of the small wind turbine? So if my repowering project is only 150 meters of tip height, I have no idea of what will be the price of my future repowering project. So it's a kind of a tricky question. Also, we have a tax in municipality. So at one moment, if the price of electricity is really low, the tax could become kind of, let's say, an incentive to not continuing the operation because it becomes too high. And also, last point, can I have a permit for my old wind farm for operating beyond 20 years? This is not always a case and not always easy to get. So what I mean is comparing the two scenarios, so the two solutions at year 15, it's a challenge actually. But if there is a way to help the operators to keep all the assets, which are, to my point of view, necessary for the objective of the region in terms of renewable assets. So we have to find a way to find it. It helps to limit environmental impact by extending lifetime, and it helps also to have green electricity at lower price because there is low or no subsidy for that. For the society, it's a good thing as well. So thank you. I hope it was clear enough, and I hope you heard me enough.
Yes, perfect. It was very better. Thank you for presentation, Maxime. Maybe you can share your screen again, your presentation. We had a question about the slides related to the scenario number 2 about a rule. Yes, this one. On the end of the slide, the 4 diameter rule. The question is 4 diameter rule, or if I understand well, the 4/8 rule.
The total height of the turbine, yeah. For instance, in Wallonia, there is a rule that is existing. If you want to put a 150-meter wind turbine, you have to be 4 times that high to the closest, let's say, zone of habitation. So it means for 150-meter turbine, you have to be 600 meters from a zone where there is houses. This is specific to Wallonia, actually. And if you go to Flemish region, this rule doesn't exist. If you go to France, this is a different rule. This is 500 meters. It's a fixed rule. But it means that if you want to put a 200-meter wind turbine, you have to be 800 meters from the houses. So as we know that Belgium is not, it's kind of dense in terms of houses, and then the highest you go, and then the highest you need to, the highest you need to be from the houses. This is a huge constraint because it's not because you put really huge turbine that your impact in the house will be that huge as well. In terms of noise, that we know that a big turbine doesn't make more noise than a normal wind turbine by 150. In terms of shadow, there is a regulation imitating this, let's say, this impact. 30 minutes a day maximum, 30 hours a year maximum at each point. And in terms of landscape, that we know that if we put bigger wind turbines, the number will be lower because we have to respect a certain distance between each wind turbines that is linked to the diameter. So this rule actually is kind of a constraint for repowering project.
Okay, thank you for your very complete answer. Wim, maybe you can put your camera and micro. Yes, perfect. I think you had many questions also.
Yeah, well, thank you very much. It was a very interesting presentation, Mr. Kelder. So maybe a first question here. So when you're looking at the lifetime extension, the repowering, what is the number of additional years that you are aiming for?
This is really a specific question, specific to each wind site. So that we know for those 2 wind farms that, structurally speaking, that we know that they will not fail, let's say, before 25 years, or even a bit more for some of them, depending on the turbulences on each wind turbine. So this is the number we have. A big part of the job is assessing the OPEX forecast beyond 20 years, where we have to sign and prepare kind of a new maintenance contract, where you have, as an operator, have to take more risk than before.
Yeah.
So there is no specific figures to give you today.
Yeah, okay, but following up on that question, of course, so which kind of, because it's you said that it's difficult to find contractors or to try to contract that, so the OPEX is unclear. So have you already identified some technical challenges that are making this hard?
I don't say you will not find any players. You will find it. You will find the one who will propose you a full omnium, but a huge price you will not be able to pay. And that's one thing. Or you find other players, but they will put a part or a huge part of the risk on your side. Actually, within Luminus, which is part of EDF Group, we have an affiliate who can help us with that. So we are working with our affiliates and try to make the good balance between the risk between them and us. So it helps us indeed to let's say to operate in the kind of good price, let's say a reasonable price of OPEX and reasonable risk as well.
Yes, so it's all about balancing this. It looks like a very complex comparison and not easy to perform. So I understand that now you're really focusing on the financial side of this. On the other side, you have also, by extending the lifetime of these windmills, you also said is okay. It also means that it's also a more durable or not more durable. So there is an impact on, you have extended material use also. So the question is, have you tried or considered calculating the differences in CO2 footprint between the lifetime extension or the replacement?
No, I did not do any calculation, but it can be done, but I have no figures close to me actually.
Yeah. Oh, okay, yeah, but
quite easily.
just, okay, thank you very much. I don't have any questions, so Paul, please.
Yes, but thank you. First, thanks to the speakers, of course. Thanks, Wim, for this collaboration also, and thanks to all participants. I think we can ask everybody to don't hesitate to send us a feedback or a question. If there are still questions, we can put you in relation. And please also follow our activities. I have no other things to say, but we will send you, of course, the presentations and the video of this webinar. I hope it was good for you. Wim, if you have still words.
No, let's also express my thank you to all the speakers, to you, to Cluster Tweed. Thank you for the very nice collaboration, and everyone, thank you for watching. And we are sure that we will meet again in one of the next editions on maintaining wind farms and maintaining windmills. Thank you very much. Bye.
Thank you.
Thank you.